So in this video, I'm just going to run through two geometry questions quite quickly. And the first one was done in class, not fully in the formal proof, but the logic of the proof we did go through, and maybe it wasn't written out formally, but you have kind of one method there. And as far as I can remember, it was using the idea of basically the angle standing on the same arc, and the angle at the center of the circle is twice the angle at the circle, and so on. So I'm going to do that one again, but I'm actually going to show a second method, and I think it's really important that you understand that there is, for most of these questions, 3 or 4, if not more, methods that can be used, and you can get to it. So it's just about seeing something that's useful. Now, bear with me. For the method I'm going to use here, I'm going to need perpendicular lines, but obviously I find that very difficult to draw when I'm using the computer. So first thing I'm going to do is I'm going to identify the fact that AB is actually a tangent to the circle. So if I drop a line here, it's going to be perpendicular. Similarly, if I do that here, AC is also a tangent, which means that here, ignoring that little line for a second, I have two right-angled triangles, I have two right angles, one at Q and one at P. These two dotted lines, what I've created is a quadrilateral, and the quadrilateral OQAP. So what I can say is, because angle OQA, I'm just going to keep this written down as we go, that's also equal to angle OPA, and that's equal to 90 degrees, since AC and AB are tangents. Okay, so and the radius is perpendicular to the tangent. Okay, so by that logic, we have the quadrilateral APOQ, and it's not just any type of quadrilateral because the opposite angles add up to 90 degrees, it's a cyclic quadrilateral, and that's important. Cyclic quadrilaterals are going to be really, really important the whole way through. So what we can say then is, if I go, basically, if you can imagine it, and again, it's quite difficult to draw, but there's a circle that goes through all of these points. Okay, so that's a circle, and all these points are on the circle. So what we can say there then is O to Q to P is the same as O, sorry now, I need to move to another colour. So O to Q to P is the same size as O to A to P. So this angle here is the same as this angle here because they're standing on the same arc. So let's write that down. Angle OQP is equal to angle OAP, angle standing on the same arc. And we know that OAP is actually half of the full angle here. So it's actually half of that full angle here. So that's half of the angle P to A to Q. So that full angle there. And the reason we know that is because, and I'm going to end up with so many colors, apologies. We have two triangles here. And this is kind of where we were working with the proof we did in class. We have two right angle triangles and they share that side. They're both right angles. So we were saying that they were congruent, and the reason they were congruent was RHS, right angle, the hypotenuse then which they share, and one other side. So this side equals this side because they're both radius. So because they're congruent, if I'm talking about this little piece here, that little angle here, which was angle OAP, it's half of the full angle because it's matched by this angle here because the two triangles are congruent. So therefore it must be half. So by using that same logic, so sorry, I'm just going to put this in OQP. So by using that kind of same logic, I'm just going to use the word similarly, because if you can prove it one way, you don't actually have to prove it a second way. So what we can say then is by saying, well, angle OQR, so O to Q to R. So we're dealing kind of with this side of the, sorry, I shouldn't really circle it, but we're dealing with that side of the triangle and the circle. So we know that OQR then is equal to half of QBR. It's exact same logic. So apologies, now just run out of space. So adding that, so angle OQP plus angle OQR will equal to a half of PAQ plus a half of angle QBR, and cleaning that up. So if you go to your diagram, O to Q to R and O to Q to P added together, sorry, so that's kind of the first line. So added together, that actually gives us angle PQR. And pulling that half out to the front leaves us with angle. Now, we have what's called PAQ, but that is absolutely fine to write as CAB, because that's just using the bigger triangle and the vertices of that bigger triangle, and that's what they want in the actual question. CBA, so that's QED, so done. So it's just another, I suppose, method to look at. I haven't drawn in anything there on the right hand side. Hopefully you can kind of follow it. I know it's very difficult with the way that I'm sketching on the computer, but very similar to the method we looked at. We had to use very similar ideas, but it was that little bit different. We didn't go into the circle, and we used kind of both sides, the left hand side and the right hand side there. So hopefully that makes sense. But like I said, that's kind of one method in class, another method here. There's at least two other methods that I could see that you could do, and possibly even more. So as long as you're kind of able to get to it, just make sure that any logic you're following is good logic, that you're not just making something up. So now let's take a look at 2011. So you can see this is question 6b, and that's back when there was a choice. So we're going to look at this particular question, and I think it's not a particularly nice question. Like, it's quite a straightforward question, but at the same time it's a bit everywhere as well. It can be very difficult to kind of follow through and see where it's going, and you know, on the outset it looks okay, but then using P1, P2, P3, Q1, Q2, Q3, you know, that all that kind of becomes, you know, really, it makes it really, really difficult, because once you start getting into that, it's kind of, you know, you've got subscripts, it's really easy, your work gets messy, it's really easy to make mistakes. But look, let's go through it. So in the diagram, P1 to Q1, in the diagram, P1 to Q1, P2 to Q2, and P3 to Q3 are parallel. Yeah, it looks like it. And Q1 to P2 and Q2 to P3 are parallel. And they want us to prove that P1 to Q1 multiplied by P3 to Q3 is equal to P2 to Q2 squared. Okay, so I suppose once you know that they're parallel and the way that they've been presented, you should hopefully kind of at this point have figured out, well, we're actually dealing with similar triangles. Okay, and that's what we're dealing with. So we have a number of triangles that are similar to each other. So we have I'll rub this out in a sec. But we have this little triangle here, which is a smaller version of the bigger triangle here, which is a smaller version again of this triangle here. So there are three similar triangles. And we also then have this triangle here, which is similar to this triangle here. So there's only two in that case that are similar. But that's what we're going to be dealing with. So let's take a look at the first triangle. So I'm going to try go along the outsides of these. So if I go for the small triangle here. Okay, sorry now. Let me go back to pen. Okay. So if I deal with this triangle here, and this triangle here. Okay. So based on those two, we can do the idea of ratios. O to P3 divided by O to P2 is the same as O to Q2 over O to Q1. So that's kind of our first set of ratios. So then if we look at two more triangles, so if we look at, now I'll try to get this in red. If I look at the red one here, that one there, and that is in turn parallel, I'll go with light blue, to this one here. And by that logic, we can say OP2 divided by OP1 is equal to OQ2 over OQ1. Okay, so hopefully at this point you notice that the right hand side in both of these are equal. So what we can do is we can then say that OP3, OP2 is equal to OP2 by OP1. Okay. So if we take a look at what they want us to prove again, we currently have O's in there, but actually we don't want O's, we actually want Q's. So by taking both sides of this, so I'll call this my left hand side, and I'll call that my right hand side. So let's go up here. Let's take the left hand side, and the left hand side is OP3 over OP2. Now just for a second, I'm just going to rub out everything on my diagram just so we can kind of see. So what we're looking at here, so O to P3 and O to P2, so I'll do that in a different colour. That's the two sides we're talking about. Now we really want to work with the Q's, so why not look at these triangles here and say, well, if we take O to P3 and divide by O to P2, that's the same thing as saying, well, P3 Q3 divided by P2 Q2. So we basically changed that left hand side to something we wanted, and we can do the same thing here with the right hand side. So the right hand side is OP2 over OP1, and using the exact same logic we can say, well, that's the same as saying P2 Q2 divided by P1 Q1. Now I haven't drawn in the two triangles there, but we're still using the light blue triangle, and this time the second triangle is this green one here. So putting that right hand side and left hand side back together, we're now going to get P3 Q3 all over P2 Q2, and that equals P2 Q2 P1 Q1. So again, still doesn't look like what we want, but if we get rid of our fractions, we end up with P3 Q3 multiplied by P1 Q1 is equal to P2 Q2 multiplied by P2 Q2, which can be simplified or changed slightly to P1 Q1, so we've just changed the order, multiplied by P3 Q3, and that equals to P2 Q2 squared, and that is exactly what we were asked to get. So it's just using different variations of similar triangles to get what we want. So we couldn't just work straight away from the triangles there, with the ones that we have in this one. We had to work first with the ones that went from kind of the old P3 Q2, the kind of more slanty ones. We had to work with them first in order to work through that. So hopefully that's helpful. Now again, there's a few different ways you could work through it, all very similar kind of logic, but you know, you have variations within that.